As I said in a previous video, there's one specific application of ANS which I think is so important in the future that it merits its own video. That is the use of ANS to interface with the human body. The body is immensely complex. The brain, for example, as we've already said, is the most complex known object in the universe. To make sense of this complexity, we need a system which can understand it. One which can recognize these patterns inherent in the body and use them. Obviously, ANS are the best way of doing exactly this, because they are the best system for recognizing such complex patterns. Let's look at a few applications. One important application will be in the diagnosis and prediction of disease. We can measure many parameters of the body, which are called biometrics. For example, blood pressure, body temperature, the heart rate and its pattern, and the chemistry of blood, urine and mucus, and many other parameters as well. Can such variables predict disease or the probability of disease? Well, obviously they can, because this is how doctors diagnose diseases in the first place. But perhaps more can be diagnosed, or the diagnosis made simpler. But the patterns of biometric data which are produced are too complex to be obvious to the human observer. However, ANS can learn any pattern by example, regardless of whether humans can see the pattern or not. So imagine if we could link up an ANS system to a patient and predict whether they are on the verge of having a heart attack or a stroke. If there is a pattern of biometrics which corresponds to this, the AN will be able to identify it. We just need enough examples to train a network with and to ensure that the correct sensory data is supplied. Of course, it's always possible that a condition doesn't have any corresponding pattern, but in that case, no system will ever be able to detect it anyway. Such systems, because they're automated, could make the diagnosis of disease much cheaper than visiting a human, highly trained doctor, which is expensive. Obviously, they could also make the diagnosis of disease much more routine, because it doesn't require a visit to a designated area like a doctor's surgery in order to use the technology. A second application is in the interpretation of nerve signals, or EEG signals. The pattern of nerve impulses corresponds to, for example, movement or speech. The coding inherent in such signals is extremely complex, and again, what better system therefore to decode it than a neural network? Such a system might be used for human-to-computer interface. For example, to allow paralyzed people to interact with computers or to steer an automated wheelchair. A similar system might, in the future, allow the fine control and interface of artificial limbs and organs. We might see this developing eventually into true human-to-machine integration, or even, perhaps in the future, human-to-human integration.